Okay, the last set of notes is on oceanography, waves, tides, currents, and life forms. I know it sounds like a lot. I think it's a total of 14 slides. We're going to break this up in class, so if you could take all the notes, that would be fabulous. If you can at least get half of them done, that would suffice for now. Okay, how do waves form? Wind has to blow over smooth water. Oh, wait, and before you even begin, you can write the words or you can draw the picture. Either one totally works. Okay, either way, wave or wind has to blow over smooth water. As the wind blows over the water, you get little teeny surface ripples forming. Surface ripples form chop. If you've ever seen out in the bay a choppy day where there's a little teeny white caps, they're like chop is just short, steep waves, and they form over time into regularly spaced swells. The swells become breakers on a distant shoreline. A breaker is a breaking wave. Okay, so they become breakers on a distant shoreline, and the shape of the shoreline affects the size of the breakers. There are 3 factors that determine wave size, or how big your wave is going to be. The first one is wind velocity, so how fast is the wind blowing and in what direction. The second factor is the length of time the wind is blowing over the open water. And the third factor is fetch, and that's the distance along the open water over which the wind blows. So if the wind is traveling in the same direction very fast for a long period of time over a large expanse, a large distance of open water, you're going to have a giant wave. Your wave dimensions will increase until they reach the maximum size for the existing storm conditions. And maximum wave dimensions, it varies. Okay. When your waves are as big as they can get, that is known as a fully developed sea. Make sure with this picture that you know the parts of a wave. The top is the crest, the bottom is a trough. From the bottom of the wave to the top of the wave is the height of the wave, and the wavelength is from one crest to another crest. Okay, waves of oscillation. The actual motion of a wave is in a circular path. There isn't really a mass forward movement of water. The energy is moving forward, but the water itself is kind of going up and down. And if you've ever seen a surfer sitting there just kind of bobbing up and down as swells go underneath him or her, or a buoy bobbing up and down along the water, they're not pushed to the shoreline unless there's some current bringing them in. All they are doing is really moving up and down. It's a wave of oscillation. And if you look at these pictures here, you can see the little ball and this little pyramid thing. They're just going up and down. Okay, there are 3 types of breakers, or 3 types of waves. First of all, we have a plunging breaker. This is where the offshore area is really steep, and the waves peak rapidly on the steep sea floor. So you have to have a very steep continental shelf in order to get a plunging breaker. This last picture here on the right is a plunging breaker. This is, it's a typical surfer wave. A spilling breaker here on the left is what we have here in Virginia Beach. These are pretty flat near the shore slope where the waves lose their energy by friction. So you have the shoreline slopes gradually, and as the wave moves along this gradually sloping shoreline or continental shelf, the waves lose their energy. So they build up slowly, and then the crest spills down the face of the wave, and then it builds up, and the crest spills down. So it's what we have in Virginia Beach. All waves contain swash, that's when the water swashes ashore, and backwash, where the water returns seaward, and it becomes the next wave. A tsunami is not necessarily a breaker. It is a giant wave. It's the middle picture here. To the right and to the left, all you see is one wave. Okay, and it's caused by earthquakes or landslides. Something happening under the water or crashing into the water will cause a tsunami. Wave refraction. When waves bend as they as they approach the shoreline at an angle, that's called wave refraction. Now, when you get the waves bending, and you can see from this picture, they're not hitting the shoreline straight on, they're actually moving at an angle. You end up getting a longshore current. It's a really weak current along the surf zone. If you've ever been at the beach, and especially when you were younger, if your parents were, letting you go out into the waves by yourself, and they told you we're sitting in front of the Purple House or the Marriott Hotel or whatever it happened to be as your kind of like guideline as to how you see them, like visual aid. If you pay attention, after you've been playing in the water for a little while, you're actually down from the hotel or down from the Purple House or whatever it means. And it's that longshore current that's pulling you along the current. It's a weak current. It's not going to move you rapidly, but you'll gradually just start moving down. Okay, the greater the angle of the wave, the greater the volume of water that's discharged. That just means that if you have more water going in, your longshore current will be a little stronger. Now, there are times, especially during storms, when the longshore current overflows and actually goes into the surf zone. Literally, your longshore current, instead of staying along the shore, because of the storm and velocity of the water moving, it literally goes into the breaker zone, and this causes a rip current. A rip current you can actually see if you're sitting on the beach. This is actually a rip current right here, where you have waves, a seemingly flat area, and then waves again. That's a rip current. If you're high up, you can see the sediment in the water, the sand or the silt, whatever happens to be in there. You can see that that is carried away with a rip current. Okay, that was it for waves. Now we're on to tides. It is one slide. That is it. Draw the picture. Okay, you have to remember that tides are caused by the moon's gravitational pull. When the moon is in alignment with the Earth, that means on the right or the left of the Earth, then you're going to have a high tide. The gravitational pull on one side by the moon causes all the water to bulge out. Okay, so that's a high tide. On the other side, you can have the sun's gravitational pull pulling the water. In between the high tides, the high tide areas where the water is being pulled out to the right or left, you have low tide, and that's going to be, in this case, at the top and the bottom. Okay, ocean currents. I think it's 3 slides long. A surface current is caused by wind patterns. They can be several hundred meters deep, and their temperature depends on where they came from. If your current is coming from the poles, it's going to be cold water. If it's coming from the equator, it's going to be warm water. Surface currents create a gyre. A gyre is just a circular pattern that rotates just like the wind patterns. Think Coriolis effect. It's going to be clockwise in the northern hemisphere. Okay, examples of surface currents are the Gulf Stream or the EAC. A deep ocean current is caused by difference in density of the water. Cool or cold and salty water are very dense. The densest water lies off of Antarctica and flows north. Okay. Deep ocean currents always flow in opposite directions of your surface current. If a surface current is flowing south, the deep ocean current under it is moving north. If the deep ocean current comes close to the surface, you have something called upwelling occur. And upwelling it's honestly a really great place for commercial fishermen to be, because you have this nutrient-rich food stuff from the bottom of the ocean. Where is it? Where's my mouse? Right here. You have nutrient-rich food from the bottom of the ocean coming up. It literally rides along the slope or the shelf in some cases, and it literally pulls the nutrients up here, and this is where you're going to have a lot of fish feeding. Okay, the ocean floor was originally measured, think way back in time, 1872 was the first expedition. It was measured with a depth of wire. Literally, somebody was sitting there in a boat. They let all the wire out. When it reached the bottom, they marked the depth. They pulled it up. They moved the boat. They put the wire back down. Okay, not a very accurate way of finding the depth of the ocean floor or even finding what the ocean floor looked like. Now we use echo sounding, radar sonar, and seismographic surveys. CSAT, that's one you definitely need to know, is a satellite that has made the most complete picture of the ocean floor. And this is it right here. So CSAT is up in space. It's hanging out in the exosphere. It sends a satellite radar down. The signal measures the height of the sea surface. The water surface tends to follow the seabed structure. So you can see here, if the seabed rises up, the water rises up. And this is like in times that there aren't like big storms. Think a nice calm day. Okay, that was it for mapping the ocean floor and for surface currents. Now we're on life zones. I think there's 4 slides, and that's it. Okay, forms of life that you need to know, and you need to know anything in bold. Okay, first of all, the largest group of animals and plants in the ocean are called plankton. Plankton float. They float at the surface and can be found where the sun penetrates. They're the main food for larger organisms. Nectins swim. So if there's anything in the ocean that can actively swim, search for food, avoid predators, that would be a nectin. So plankton float, nectins swim. Okay, an example of nectins: seals, dolphins, sharks, barracudas, whatever. If it swims and can find its own food and avoid predators, it's a nectin. Benthos live on the bottom of the ocean. Benthos bottom. They live on the ocean floor. Plants, crab, barnacles, those are examples of benthos. Plankton float, nectins swim, benthos are on the bottom, the ocean floor. Okay, is a life zone called the intertidal zone. This is literally the zone between the low and the high tide lines. So it's submerged in water at times, then it's dry, submerged, dry, submerged, dry. It's the most changeable zone. It's very difficult for organisms to survive here. The waves and the tides cause a lot of movement. You have the periods of wet, the periods of dry. Pretty much anything super hardy is going to live here, like anemones, crabs, mussels, seaweed, flounder. The neritic zone is from the low tide line to the edge of the continental shelf. It's where sunlight penetrates and the temperature stays fairly constant. This is the most rich in life. This is where your fishing grounds are. Most of your main types of fish are literally in the neritic zone. We have the open ocean zone, which has a photosynthetic zone at the top. If light can go down, okay, then it's a photosynthetic zone. The bathyl zone is below the photosynthetic. That's where no sun and no plants are found. And then we have the abyssal zone. It's the deep dark zone. It's literally at the bottom from 2,000 to 6,000 meters, sometimes farther than that. There's no sun, little food. You have the critters that live down there are smaller than their counterparts up in the photosynthetic or bathyl zone. There's very high pressure. And that's it.